Okay. You okay, Bubba? All right. I know I was about a minute late getting that link posted, so I will give a few seconds for folks to arrive before we get into the actual material. But today we're going to take what we learned about parametric curves, namely just what they are and how to graph them, and we're going to start doing calculus operations. It's not too hard. In fact, it's really easy. A lot of it is more intuitive than working in other settings, so I don't think you'll have any sort of difficult time with it. So let's do it like this, and then like this, and then a little bit like that. And some of these. Okay. Oh, we're gonna have to go with one of these. So let's try this one. Okay, so I know tomorrow is Thanksgiving. I really do appreciate you guys getting up early the day before and being here for lecture. That shows a kind of dedication that is really necessary at this level, and congratulations for holding on to that. Today we're going to talk about calculus with parametric curves. That's the game. This is section 10.2. And if you'll forgive me, I'm going to go let my cat in because out. Whatever it is you assholes want. What are we doing, gang? Can we figure it out? I got one calling to get in, two standing on the other side to get out, and I'm trying to teach. Y'all motherfuckers gotta figure out what you want. I think they're with you for now, baby. I'm sorry. I guess the nice difference between animals and children is that I can curse at the animals all I want. They don't know what the hell I'm saying, so I don't feel as bad doing it. I'm gonna have to get out of the habit. So today, calculus with parametric curves. I think if anything makes this section difficult, it's just not being comfy with the previous section. So is there anything to do with the last section, just graphing parametric curves, that we would like to talk about a little bit more before I show you? They definitely understand like tone and inflection. They understand a few words, and absolutely, they choose to be assholes instead. Yeah, no doubt, no doubt. Especially the black cat. The white one's just a little stupid. Okay. Yeah, so like I was saying, the only thing I think that could even create any challenge here is difficulty with the previous section. So is there anything that we'd like to look at from 10.1? Graphing parametric curves or coming up with a parametrization? Would we like to look at another example or two in Desmos? Anything like that before we let me give you an example in Desmos here. Let's pick something a little wild. We'll just take a look. So I know of one or two kind of fun, exceptionally wonky examples. Oh yeah, we said we were going to do the cycloid, didn't we? Yeah, this will be a good introduction. All right, let me show you the cycloid. I have to pick an R. We'll do 1t minus sine t and 1 minus cos t. All right. So I'm about to show you a parametric curve. Yes, I do want that slider. Yes, 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 please. All right, and then we're going to do this comma 1 minus cos t. This will make it easier for me to to kind of help you imagine what's going on with the parametric curve. Yeah. So this is the x function that I'm going to use. So I'm going to sketch for you a parametric curve here, but I want to help you see it as this sort of motion. So we'll go to how about 6 pi step size 0.01. Here's this particle moving. You see it? Look at it go. And now it's going to come back. So this is really what a parametric curve is. It's a particle moving along a path. And in this case, the path is what's called a cycloid. Can I get this to show without? This is like it's not wanting to play nice in the same way it did last time. So if you imagine the path that this thing takes, that is your parametric curve. And one of the things that I'm going to teach you guys how to do today is to find the length of a parametric curve. Another one I'm going to teach you how to do today is find tangent lines to parametric curves, neither of which are hard. They're both pretty straightforward. And the trick, I think, to graphing these things is really just to think of the parameter t as time, and to be genuinely comfortable with this idea of a particle moving around on the curve. All right, that's enough of that. The particular curve I'm showing you here is called a cycloid. And normally I do go through the derivation of this curve, but I think it doesn't really help us with what we're trying to do. So just let me show it to you as an example. I'll try to move through it quickly. One last. From 10.1. So if you can picture that particle doing what it was doing there, kind of the way that you get that curve is by starting with a circle and kind of tagging a point on the circle. Think of this as like a reflector on a bicycle wheel. And if the center of the circle is moving forwards like this, then you can imagine a little bit later, you know, maybe my tagged point will be up here. Here's the center still moving. A little bit later, the tagged point on the center of my circle is up here. The tagged point on my circle is up here. The center is there, and so on, right? So this sort of motion produces the curve that's called the cycloid. And rather than going through the lengthy geometric derivation here, I'll just kind of draw one for you. Right, looks like this, and then it would continue on. And so on. The coordinates, the parametric equations for this curve, x of t, depends on the radius of the circle you're playing with, is r times t minus sine t, and y of t is r times 1 plus 1 minus cos t. And normally in class, I go through these, the derivation of these equations based on the geometry described here. But I don't think, like I said, I don't think it's really going to help us with any insights. If anything, it just serves to confuse. But that tracked point, that particle, kind of moves like this as t increases. And what I want to talk about today the reason this makes a nice example is how to find, for example, horizontal tangent lines or points along a curve where you'd have a horizontal tangent. So today we begin with finding tangents, specifically horizontal tangent lines and vertical tangent lines. So if you look along this curve, you'll notice there's a few places where the tangent lines are horizontal. All right, like right here, should have a horizontal tangent. Right here, I should have a vertical tangent, right? Because as you get closer and closer to this cusp, my tangent lines are getting really, really, really close to vertical. So at that cusp, my tangent line would be vertical. And then over here again, I'll have another horizontal tangent. And since these are periodic, since they repeat, anywhere you have a cusp like this, or a top of a hill like that, you would have a vertical or horizontal tangent. Yeah, so the 5-minute review from Monday, if that's what we want here, is just parametric curves come from parametric equations where instead of y being f of x, x is x of t, and y is y of t. So I give you two different equations, one for x, one for y. Maybe say it like this: x is equal to x of t, y is equal to y of t. And I give you some time domain, like a is less than or equal to t is less than or equal to b. And the graph could look like any sort of wild shit, really. Over here, the point where you start would be x of a comma y of a. And up here, this would be x of b comma y of b. And you think of it like a point moving along a path. All right, that's all. So this is what parametric curves can look like. Oh shit, is my zoom better not freeze. All right. So this point we call the initial point. This point we call the terminal point. And you think of this as being a path that's walked by a particle whose x coordinate satisfies this equation at any time t, whose y coordinate satisfies this equation at any time t, and t is allowed to run from a to b. The main advantage here is that x isn't a function of y isn't a function of x. So you can get all sorts of wonky looking curves. You don't need to pass the vertical line test. They don't need to pass the horizontal line test. All right, I don't really have time to go a whole lot more reviewing than that, but take a look at the examples in the textbook, right? The examples in 10.1 are good. Okay. So the two calculus operations I want to do with parametric curves, we can do more. But there's two that are interesting. They are tangents and arc length. Sometimes I don't even teach arc length back in chapter 8. I just teach it here in chapter 10 because I think arc length makes so much more sense here. Tangents are also kind of interesting. The basic idea is this. For tangents, dy dx, which is the slope of the tangent line,
can be calculated as dy dt over dx dt. So if you want the slope of a tangent line to a parametric curve, you differentiate the y function with respect to time, you differentiate the x function with respect to time, and then you divide those by each other. It's almost like you can cancel the dt's. Of course, dy and dt, dx and dt, those are not real numbers. They're infinitesimals, they're differentials. You cannot cancel them, but symbolically it works out like you could. Arc length, your arc length integral is a time integral now. I'll still use the symbol s for arc length, and this is the integral from t equals a to t equals b of the square root of dy dt squared plus dx dt squared, all done dt. I'm going to go through a little derivation of the arc length integral for you because it's kind of neat to see how it relates to the one we did back in chapter 8. But the tangent thing doesn't really deserve any sort of derivation. It's just a small change in y over a small change in x can be thought of as a small change in y over a small change in t divided by a small change in x over a small change in t. This is utterly trivial. But before I dismiss the tangent thing as being trivial, just give you a formula and walk away, I want to do a few examples here. So I'll show you how to find like the point here where you've got a horizontal tangent line, the point here where you've got a vertical tangent line, the point here where you've got a horizontal tangent line, the point here. So let's do that. Okay, we'll do an explicit example with tangents first, then I'll cook up that arc length formula for you. I'll leave this here for a second if you're writing over this. This isn't calc, is it? It's pre-calc. Yeah, okay. So if you want to find the slope of the tangent line, you differentiate the y function, you differentiate the x function, and then you divide them. The thing to be careful of here, the variable in this expression will be t, not x or y. So when you start working with this derivative, whatever it is you want to do, setting it equal to 0 or plugging something in to try and find a slope at a certain point, you're going to be working with t values, which are values of the parameter. And one of the most common mistakes people make is forgetting that there is no t-axis in this picture. Right? This is still the x-axis. This is still the y-axis. So if I ask you for the point where you have a horizontal tangent line, first you need to find the time, the t value. Then you need to plug that t value back into the original set of parametric equations to get the point x comma y. So I'm going to grab an example here from your textbook. Brachistochrone stuff is neat, but what's neater is this. Yeah. Second derivative stuff, curvature stuff, I'm not even going to bother with here. Right, okay. Yeah. We'll do example 1. So we've got a set of parametric equations. I want to first, given x of t equals t squared, y of t equals t cubed minus 3t. I want to do a few things. I'm going to do them out of order here. I'm going to find dy dx, find points x comma y with horizontal tangents, find points x comma y with vertical tangents, and then D, we'll find the two tangent lines at 3, 0. So we've got a nice list of tasks here. I'm modifying the problem a little bit, just working with the curve they gave us, so we can do some simpler things and then also the things they asked for. So to solve part A, find dy dx for any parametric curve, you just have to remember that this is dy dt over dx dt. All right, and you do have to remember that. This is not something that you're going to see on a formula sheet. It's not something I'll include in the problems. You need to remember that dy dx is dy dt over dx dt. Symbolically, it makes great sense, and it's really just a consequence of the chain rule. There's nothing crazy going on here. So dy dt, the derivative of the y function taken with respect to time, is 3t squared minus 3. And dx dt, the derivative of the x function taken with respect to time, is just 2t. So that's part A done. Now, for part B, I'm going to solve part B. Horizontal tangents, which I'll abbreviate HTL, these occur when the slope of the tangent line is 0, right? Well, that's when dy dx is 0, because dy dx, just like back in Calc 1, is the slope of your tangent line. Again, the catch is here that dy dx is going to look like a function of t. So rather than getting x values out of this, you'll be getting t values out of this. So this means we need to solve 0 is equal to 3t squared minus 3 over 2t. And we can solve that by factoring the 3 from the top here. This is 3 times t squared minus 1 over 2t. So dy dx will equal 0 when t squared minus 1 is equal to 0. And since this factors as t minus 1 times t plus 1, these happen, or this happens, when t is equal to plus or minus 1. Everybody with me so far? The essence of it is to find horizontal tangent lines, you set the top equal to 0. It's a little bit more subtle than that because the dy dt from the top can interact with the dx dt in the bottom. So what you should do is take your dy dx, set that whole apparatus equal to 0. This is now a rational equation of the type you learned how to solve very carefully in pre-calculus. Now, it may have been a while, so I'll remind you, a rational expression like this is equal to 0, provided the top is equal to 0, and the bottom is not equal to 0. It's important, that last bit. If the top and bottom are both equal to 0 at the same time, then you need to dig in with limits and investigate. But if the top is 0 and the bottom is not 0, then you can be confident that this fraction, which is dy dx, is 0. So here I factor the top and set it to 0. I get these 2 times, plus and minus 1. Those are not points. They're not even x values. They're t values. And since I want points, x comma y with horizontal tangents, I need to plug these t values back in. And the points will be x of 1, comma, y of 1, and x of -1, comma, y of -1. All right, if you recall, the way we find points on the graph of a parametric curve is by plugging t values into the x and y functions. So I want to find the point on the graph associated with t equals +1. So I'm going to plug t equals 1 into both the x and y equations. X of 1 is just 1 squared, and y of 1 is 1 cubed minus 3 times 1. 1 squared is 1, and 1 cubed minus 3 times 1 is -2. So one of these points, this guy, he is the point 1, -2. The other one is going to come from x of -1 and y of -1. X of -1 is -1 squared, which is 1. Y of -1 is -1 cubed minus 3 times -1. That's -1 minus minus makes +3. That's +2. So this point right here is 1, 2. So my 2 points where I have horizontal tangents are 1, -2 and 1, +2. And if you look at the curve here, you see it, right? Here's this curve. At 1, 2 and at -1, 2, I have a horizontal tangent. So strategically, the sort of thing you need to remember if you want to use this to solve future problems, horizontal tangent lines will occur when the derivative dy dx is equal to 0. And then you need to remember how to cook up dy dx. It's dy dt over dx dt. And then you need to remember how to solve expressions like this are equal to 0, which is a pre-calculus thing, but you might want to jog your memory a little bit. Patrick JMT has some good videos. Paul's Online Math Notes has some good pages. So if you don't remember how to solve equations like this, big rational expressions equal 0, check it out. Basically, you just set the top equal to 0, but the catch comes if the top and bottom happen to be 0 at the same time. If that happens, again, you need to use a limit to investigate. All right. Vertical tangents. Think back, use your Calc 1 brains. How do we find vertical tangents? Where do they come from? Does anybody remember what the derivative does? Yeah, good. These occur when dy dx tends to plus or minus infinity. It's not just that the derivative needs to be undefined. Derivatives can be undefined in a bunch of different ways. If you have a hole in your graph, then the derivative would be undefined. If you have any point where you're not differentiable, the derivative would be undefined. We need this particular kind of undefined, where the derivative has a vertical asymptote. The classic example from Calc 1 looks like this thing. So this guy has a vertical tangent at 0. And he does that because his derivative is derivative looks like this. The red function is the derivative of the black. So where the red function blows up to infinity, which is at 0, the black function will have vertical tangent lines. And that clearly happens here at 0. So vertical tangent lines occur where dy dx tends to plus or minus infinity. Alrighty, so let's take my dy dx here. That's still what it was before. It's 3 times t squared minus 1 over 2t. So this thing will tend to plus or minus infinity as t tends to 0. Because this 2t downstairs here, as he goes to 0, as long as the top isn't going to 0, that will make the whole thing go to infinity. So essentially, for HTLs, you set the top of the derivative equal to 0, and for VTLs, you set the bottom of the derivative equal to 0. Again, it's not always that simple. You should always write down dy dx and think about this. It's the blue box statements here that you should be careful thinking about. But yes, since this is a rational function, it's a ratio of polynomials, and the top and bottom don't have any shared factors, we can be confident saying that as the bottom goes to 0, the whole thing goes to infinity. Maybe plus infinity from one side, maybe negative infinity from another side, I'm not sure, but there's definitely only the one place it's at 0. So my VTL, so the points will be at x of 0, comma, y of 0. And x of 0 is 0. Y of 0 is also 0. So this is the origin. All right, I'm just plugging back into the original equations. Remember, x of t is t squared. Y of t is t cubed minus 3t. You plug 0 into both of those, and you get 0 out for both. And you can compare this to the picture in the textbook. Right over here at 0, 0, you have a vertical tangent line, and nowhere else. Now, the last thing I was going to ask you guys to do here is to find the two tangent lines at the point 3, 0. To do this, we need to figure out the t values associated with the point 3, 0. So that means we need to solve x of t equals 3 and y of t equals 0. X of t, remember x of t, my x function, I'll leave it right here. X of t is t squared, so this means I need to solve the equation t squared equals 3 and t cubed minus 3t equals 0. All right. Well, t squared equals 3 has two solutions. You can kind of pull the 3 over to one side and then factor as a difference of squares. That's t minus the square root of 3 times t plus the square root of 3. Or you could solve it by taking square roots. Just remember the plus and minus. So you get t equals root 3 or t equals negative root 3 out as your solutions. And t cubed minus 3t equals 0. We can solve this by factoring also. This is t times t squared minus 3, right, equals 0. And so we get t equals 0 or t squared minus 3 equals 0. T equals 0 is just t equals 0. This guy again gives me t equals plus and minus the square root of 3. So what all this work says is that the y-coordinate on my curve will be equal to 0 at any of these three t values, plus minus root 3 and 0. And that the x-coordinate of my curve will be equal to 3 at either of these two times, plus root 3 and minus root 3. You take the overlap here. You need both of these to be true. That's why I wrote the word and here rather than the word or, because for my curve to be going through the point 3, 0 means that the x value is 3 and the y value is 0. So one of them on their own is not enough. The t values that make this equation true and simultaneously make this equation true are the t values I'm looking for. So my t values, my curve passes through 3, 0 when t is equal to negative root 3 and when t is equal to positive root 3. I don't include this 0 because I didn't get t equals 0 as a solution here. If I did get t equals 0 as a solution here, in addition to here, then there would be 3 times where my curve passes through the point 3, 0. Is this making sense? All right, sweet. So then if I want to find the two tangent lines, I want to find the equations of the tangent lines, then I'm going to need to take my derivative and then plug in these t values to get the slope. So recall, dy dx, we've calculated this earlier, is 3 times t squared minus 1 over 2t. So I'll call the two slopes, call the two tangent lines, I don't know, y1 and y2 with slopes m1 and m2 respectively. So the tangent line that I'm calling y1 has slope m1. The tangent line that I'm calling y2 has slope m2. M1 is going to come from dy dx evaluated at time t equals negative square root of 3, which is 3 times t squared minus 1 over 2t evaluated at time t equals negative square root 3. So I'm going to go ahead and plug in negative square root of 3 for t into my derivative. That will give me the slope of that first tangent line, the tangent line associated with this guy. I'll call this t1 and t2 to make life a little easier, help us see where each thing is coming from. If I plug negative root 3 in here, I'll get 3 times negative root 3 squared minus 1 over 2 times negative root 3. Negative root 3 squared is 3. 3 minus 1 is 2. 6 times 2, 3 times 2 is 6. So upstairs here I have 6, and downstairs I have negative 2 square roots of 3. You can cancel the 6 into the 2, and you get negative 3 over root 3. And negative 3 over root 3, that's 3 to the 1 divided by 3 to the 1/2. That's just negative square root of 3. So my first tangent line, the tangent line associated with the time t equals negative root 3, is the line with this slope going through the point 3, 0. So the first tangent line is y minus 0 equals negative square root of 3 times x minus 3. Or just y equals negative root 3x plus 3 root 3. All right, this is the one I was calling y1. Right, this is my first tangent line. The second tangent line comes from doing the same thing, just using the second t value. So m2, this is the slope of the second tangent line, will be dy dx, evaluated at t equals root 3, which is 3 times t squared minus 1 over 2t, evaluated at t equals root 3, which is 3 times root 3 squared minus 1 over 2 times root 3. Root 3 squared is still, root 3 squared is still 3, 3 minus 1 is still 2, 3 times 2 is still 6. And downstairs, 2 times root 3 is just 2 times root 3. So this is positive 3 over root 3, which is just positive root 3. So m2 is just root 3. So the second tangent line again, I'll use my point slope formula. The second tangent line is y minus 0 equals root 3 times x minus 3, which is just y equals root 3x minus root 3. So those are the two tangent lines. Now, there's nothing too hard going on here. The thing you just really need to remember is that in the graphs of these parametric curves, there is no t-axis. T is not a location, it is a time. And you have to think about that path as being traced out as time evolves. So if you want x or y coordinates, you get those by plugging t values back into the original equation. And you'll see if you look in the book here, you've got these two. They left them factored like this, that's fine. You've got these two tangent lines at 3, 0, because the curve self-intersects there. So that curve goes through the point 3, 0 at the 2 times we mentioned. The first time this curve goes through that point is at time t equals negative root 3. And then it comes around here, and then at time t equals positive root 3, it hits this point again. So you've got a tangent line for the curve the first time through, and a tangent line for the curve the second time through. Any questions on this one?
Yes. So in that second, that y2 right there, why is that just the square root? Like, why is it just minus square root of 3 and not 3 square root of 3?
Oh, it should be 3 root 3. Yeah, sorry. Yeah, no, you're correct. You're absolutely correct. Yep, we got to distribute the square root of 3 here. So it'd be root 3x minus root 3 times 3. Yeah, you're correct. I'm sorry. That's a little too far to see anything, isn't it? Other questions? Okay, then there's one other thing I want to talk about. The tangent problems here are not difficult. The other thing that's really neat to look at in this setting is arc length. So I want to show you where that arc length formula I gave you comes from. because the derivation is kind of neat. So I claim that if you want to find the arc length of a parametric curve, x of t and y of t, focus you should, this is how you do it. You integrate from time t equals a to time t equals b, the expression square root of dy dt squared plus dx dt squared. You begin with your parametric curve. Which could look something like this. And over here is t equals a. So this is x of a comma y of a. That's your initial point. And your terminal point over here is x of b comma y of b. And remember, this is happening as t goes from a to b. This is the x-axis. This is the y-axis. So it's not like this is a and this is b as x values. Those are t values. But if you take the time interval, so you imagine I have a t-axis somewhere off to the side, you take your time interval a to b and you chop it up into a bunch of little pieces. Into n equal length pieces, each of length delta t, which would be b minus a over n, because they have to be equal length. So this would be, call it t0, and then t1, t2, t3, t4. b I would call tn, and so this would be tn minus 1. You can kind of think of this as a slider. You can move back and forth, and as you move that slider, your point moves around on this curve. This slider is not a part of the geometric space here. It's totally separate. So each one of those t values is going to correspond to a point on the original graph. And they're not necessarily going to be equally spaced on the graph. They're equally spaced in time. So the time it takes to travel from one point to the next is the same. But that doesn't mean that their geometric spacing is equal. And then, just like we did before, you approximate the arc length on each of those little time intervals by a straight line segment, with the understanding that as n goes to infinity, and you use more and more and more of these, the actual arc length will get closer and closer and closer to this blue arc length, this approximate length. So this is the idea. This first point down here, the initial point, I'll call that P0. And then this would be P1, P2, P3, P4, and so on. This guy I would call Pn. The guy right before would be Pn minus 1. And you get the idea, right? P5. Just like before, we're going to look at the length from one of these p's to the next one. So if let me use this guy as my kind of archetype here. I can look at a little right triangle. Call this delta yi. and call this delta xi. The difference here is that delta x is not constant throughout, right? Some of these points, the x and y distances both vary because it's the t interval that I've chopped up into equal length subintervals. So the distance from pi minus 1 to pi, the straight line distance there, squared is equal to delta yi squared plus delta xi squared. This right here, this blue distance would be the distance from P4 to P5. So you just use the Pythagorean theorem to say that this hypotenuse is squared is the sum of the squares of the side lengths. And then you can take square roots. So the distance from the I minus 1 to the ith point is the square root of delta yi squared plus delta xi squared. And then you can sum. You can say that the arc length is approximately the sum from I equals 1 to n of all these little lengths, which is the sum from I equals 1 to n of these square roots. And then we do some algebra fuckery to make this look like a Riemann sum. I'm going to switch back to purple here. I multiply and divide by delta t. And I get that this is equal to the sum from I equals 1 to n. One of those delta t's, the one from the denominator, I'm going to stick inside. Oh, shit. This should be a yi squared plus delta xi squared. And then I shove the delta t from the denominator inside as 1 over delta t squared. The other delta t stays outside the square root. So we've seen this before. If I treat this as the square root of delta t squared, I can move him inside the square root. And then I'll distribute this over these two things, giving me the sum from I equals 1 to n of the square root of delta yi squared over delta t squared plus delta xi squared over delta t squared with a delta t over 1, which is just delta t left on the outside. And now this does start to look like a Riemann sum. As delta t goes to 0, as n goes to infinity, this is going to become dy dt, this is going to become dx dt, and this is going to become dt. So this is a Riemann sum as n goes to infinity. Don't do this to me, pen. Delta yi over delta t goes to dy dt, and delta xi over delta t goes to dx dt. So the exact length becomes s equals the integral from a to b square root of dy dt squared plus dx dt squared all times dt. That's it. And you just compare this integral to this Riemann sum, right? They look very similar. That's for good reason, because that Riemann sum is the Riemann sum for this integral. I like the way of thinking about it here because to me this feels more like the Pythagorean theorem, right? It's a square root of, change in y squared plus change in x squared. That's very intuitively a little length to me. This, in other words, this looks just like the regular distance formula. Yeah? You're just integrating a bunch of micro distances, really, really, really teeny distances. And that'll give you the total distance. This makes great intuitive sense. The textbook has some reasonable pictures somewhere, I thought. Ah, shit, maybe they don't. Oh, yeah, here it is. Yeah, here we go. Now, they cook this up as a consequence of the expression we had from chapter 8. I'm really not a fan of that. I would much prefer cook this up directly like we did. I think that's much, much better. But the nice thing here is that each of these looks like a little Pythagorean triple. Looks like something that comes right straight out of Pythagoras. And it is. It does, according to exactly what we just did. They use a totally different attack to get this, but the result is the same. So if you want to get the arc length from time t equals a to t equals b, you just compute this integral. A few of these you'll know how to do right away. You'll know what to expect and everything. Like this guy is the unit circle. We saw that last time. If x of t is cos t, y of t is sine t, then you should get the circumference of the unit circle. Ah, good. Yeah, continue to annoy people with Gabriel's horn. It's a great thing to think about. So rather than going through the circle example here, which is pretty trivial, let's find the length of one arc of the cycloid. And I'm going to use t as my variable rather than theta like they're using here. X of t is t minus sine t. And y of t is r times 1 minus cos t. All right, so I'm going to come back here. This is the cycloid generated by the revolving wheel of radius r. It looks, I'll draw a small picture in here. Chop this up into bits. Try to make this look decent. Looks like this. All right, now we continue on like that forever and ever, amen. But I just want one arch. Okay, so I'd like to find this length here. So I need to know what t values are associated with the start and end point of the piece that I want to find the length of. And that means I need to find the first two solutions to this thing equals 0. right? So if you plug in t equals 0 here in the y equation, you'll see right away the cosine of 0 is 1, so this is r times 1 minus 1, that's 0. So this first guy is definitely t equals 0. When is the next time that cosine is equal to 1? Yeah, so we see that the first two solutions to y of t equals 0 are t equals 0 and t equals 2 pi. So these have to be 0 and 2 pi respectively. Now, if I want to find the length, that means I need to plug into this formula. My lower bound of integration will be 0, my upper bound will be 2 pi, but I also need dy dt and dx dt. So here, dy by dt, the derivative of this function taken with respect to t, that r is a constant multiple, he'll come along for the ride. 1 differentiates to 0. The derivative of cosine is negative sine, so this will be 0 plus sine t, or just r sine t. And dx dt, if I differentiate this guy, the r, again, is a constant multiple to come along for the ride. Derivative of t is 1. Derivative of sine t is cos t, so this is 1 minus cos t. And one of the things that I always found interesting about this curve is that the time derivative of x is y. That is a neat property. So the arc length is s equals integral from 0 to 2 pi, the square root of dy dt squared, which is r sine t all squared, plus dx dt squared, which is r times 1 minus, cos t. Squared dt. So this s, this integral here, is equal to integral 0 to 2 pi square root of r squared sine squared t plus r squared times 1 minus cos t squared. I'll write it like this so we can kind of see dt. Sorry about that. And at a glance, this integral looks a little intimidating, but you notice you can factor out an r squared. That r squared will come all the way out of that square root as an r, and that r can then come out of the integral. So we'll have integral 0 to 2 pi with an r out front. And then inside will be the square root of sine squared t plus, now I need to FOIL this out. That's 1 minus 2 cos t plus cos squared t. dt. We're lucky in a sense because we have a cosine squared plus sine squared. That's nice. We know that that adds up to 1. We're unlucky in the sense that there's other stuff to deal with. And this integral looks a little bit tricky at a glance. So let me move this up, give us some space to play with. That's equal to r integral 0 to 2 pi square root of sine squared plus cos squared and then plus 1, and then minus 2 cos t. And sine squared t plus cos squared t, that's 1. This is a t in here. So I get r times integral 0 to 2 pi square root of, this is a 1. So I've got 1 plus 1, that's 2, minus 2 cos t. Any ideas how to do this integral? I've mentioned these arc length integrals can be challenging. Does this remind you of any formulas? So I might say recall sine squared theta is 1/2 1 minus cos 2 theta. This implies that, so we're going to use a half angle identity here. This implies that 4 sine squared theta is 2 times 1 minus cos 2 theta, which is 2 minus 2 cos 2 theta. So that's 4 sine squared theta. So this kind of reminds me of this identity. Now I'm going to massage this identity until I turn it into this. The last thing I need to do here, I've got 2 minus cos 2 theta. I don't need this extra paren at the end, sorry. Is plug in theta equals t over 2. Then I'll get 4 sine squared t over 2 equals 2 minus 2 cosine 2t over 2, which is just t. So this thing under my square root here two minus 2 cos t is really just equal to 4 sine squared t over 2. And it's coming from that half angle identity. So this is the integral r times the integral from 0 to 2 pi square root of 4 sine squared t over 2 dt. And since sine squared happens to be positive, you can go ahead and take the square root here, and this will be okay. Sine t over 2. So the 4 can come out as a 2. And if you're being careful here, you would write this as the absolute value of sine of t over 2 dt, right? When you take square roots of x squared, you don't get x, you get the absolute value of x. We need to verify that this function is positive on this interval. What does this function look like? Sine of t over 2. Well, it's my regular sine function stretched out by a factor of 2. So the period here is actually 4 pi. makes this 2 pi, which makes this pi, and makes this 3 pi. So the sine of t over 2 looks like this. And from 0 to 2 pi, that is indeed positive. So I can ditch the absolute values. And now this is a little u sub problem. So I would let u equal t over 2. du is 1/2 dt. I do need to change my bounds. 0 stays 0, and 2 pi is going to become pi. So I'll get another 2 from the differential. So this will be 4r integral 0 to pi sine of u. And then dt, remember, is 2 du. I already brought the 2 out, so this is just a du that's left. An antiderivative for sine u would be negative cosine of u. And we'll evaluate that from 0 to pi, which is going to be 4r times negative cosine of pi minus negative cosine of 0. That's 4r times, the cosine of pi is -1, so that's -1, which is 1, plus the cosine of 0, which is 1. So we get 4r times 1 plus 1, that's 8r. Some of the arc length problems in this section involve some very tricky integration. So I think you'd all agree that this trick that we did here to rewrite this integral like this is pretty sneaky. I made you guys work with trig identities back in chapter 7, but I don't think I ever made you work quite this hard. So you may want to sharpen some of those trig identity and general algebra skills by very carefully working the arc length problems in this week's homework. Now, I apologize for not having homework open on Monday. I didn't get it open until around my office hour time yesterday, which was noon, because I forgot to publish it. I've been busy. So if you do need more time on anything, as always, don't hesitate to ask for more time. Just be aware that I cannot take late work after the final. So your final exam is going to be on, say it one more time. Your final exam is December 7th at 8 a.m. That is the absolute latest I can take any homework. So I'll start any extension requests that come in from now on. I'll just push them all the way to that date. And I think that's about it for today, gang. Arc length and tangents in this setting where you're dealing with parametric curves, not terribly hard, but do make sure you take the time that 10.1 deserves. 10.2 is not anything fancy or hard. It's really just formula work. But 10.1 deserves your love. 10.1 deserves you to take some time and make sure you really understand what parametric curves are, how to sketch them by hand. It's just plotting points, but remember the t-values don't show up anywhere on the graph. The t-values are times, the graph is points x comma y. So like we did last class where you make that table with 3 columns, one for t, one for x, one for y, make sure you do a handful of those by hand carefully and until you feel comfortable with what's going on. Play around in Desmos. I invite you to do what I did at the start of the class here, putting things in Desmos and watching the point move around. It can be really illustrative. But that is it. That's all I've got for you guys today. Is there anything that you guys would like to ask before I let you go? I don't have a strong preference either way. I think I'll be making a turkey this year, but I'm cooking for my dad, and he likes ham, so I might end up making a ham. I'm not sure. He bought the meat, so I haven't be driving down to visit him. Yeah. All right. Hope you guys have a lovely holiday. Thank you again for coming. If you do have any questions, remember you can reach out via email or Canvas messages. I do have normal office hours today. I will not have an office hour tomorrow, of course, obviously with the holiday, or Friday. So if you guys need to talk, come see me in office hours today or send me a message. That's all.